Let's say y is a function of x. And like normal, we can write it as y equals f of x. So this is explicit. We call it the opposite of implicit. We say this is an explicit relation. And it's very clear, it's explicitly written how y depends on x. Now the opposite of that is implicit, and that will be our main discussion for today. Well, in this case, y still depends on x, but we cannot write it in that nice form, y equals f of x. I don't like that. There we go. But it can't be written in the form y equals f of x. It's not possible to have just y on one side and things involving only x on the other. It's some complicated mixture of x and y where we can't separate them like this. Oh, that's a comma. Okay, this is called an implicit relation. So y still depends on x, but it doesn't come in this nice little tidy explicit package. So an example of an implicit relation be something like this. Okay, so y still depends on x. When I plug in a number for x, y will have to be something because I've said that this expression is equal to 0. So that puts a restriction on y. So y depends on x, but am I going to be able to do algebra to solve for y, to get y by itself, and some expression in only x on the other side? No, it's not possible from this. So this is an implicit relation. So can we still take a derivative? That's the question. When y is implicitly in terms of x, we can still find dy dx, the derivative, through what's called implicit differentiation. Hence the title of this section. So it's all about finding the derivative dy dx when we have a complicated relationship like this, where you don't have this nice tidy y equals f of x. So here's the trick. You take the derivative, applying the derivative operator with respect to x of both sides. And sometimes we're going to use chain rule, and I'll explain. And then we will use algebra to solve for dy dx. Dy dx is going to come up in this chain rule part, as we'll see. So that'll show up. And then once we have that, we'll do algebra to solve for it. Okay, a few examples here. We want to find dy dx, the derivative of y with respect to x, when we have this relationship. It's actually a circle if you graph it. Circle centered at the origin of radius 5. Now, maybe it's a little bit of a stretch to say that this is implicit, because technically you could solve for y with the whole plus or minus square root thing. This is not exactly a function, fails the vertical line test, but this still suits our purposes. It's still a little bit complicated. So what we do, take the derivative of both sides, the derivative with respect to x. It can be easy to forget this side, but we do have to do it, and it's 0, the derivative of a constant. So what happens over here? Well, it matters that x is my variable. So when I encounter the x squared, I treat that as normal, just 2x. But what's going on with y here, so I'm taking the derivative with respect to x. Well, y does depend on x. It's just not super explicit. So we think of this as a function of x, even if it may not quite literally be a function, but close enough. So think of it as there's some function living inside y, and then this is a chain rule problem, because I have this outer thing happening, the squaring, and inside y lives this implicit relationship to x. So that's what I mean by chain rule. This is like the outside derivative part. Bring the 2 down, power rule. And then you multiply by the derivative of the inside. That's the derivative of y with respect to x. So that was chain rule that I just did there. Y depends on x, so think of it as there's some x relationship hidden in there. And so we took this outer derivative part times the derivative of the inside with respect to x. So that's how dy dx shows up. Whenever you're taking the derivative of a y part, it'll pop out. So now the goal was finding this dy dx, so we do algebra to solve for it. So subtract 2x from both sides. And divide by 2y. Okay, 2's cancel. So we get negative x over y. Okay, we'll want to get some more practice in. to find dy dx for 8 times the square root of x plus 10 times the square root of y equals 3y. Now here it's really clear that this is implicit, that there's not really a way to solve for y. Y equals in some expression that only involves x. So to find dy dx, we apply the derivative operator to both sides, derivative with respect to x. And whenever I encounter a y, I will first take its derivative like normal, but then multiply by dy dx, because that's chain rule. But when I encounter an x like this, well, there's no dy dx that shows up. It's just taking a normal derivative. So doing power rule here, remember that the square root of x is the same thing as x to the 1/2. And when I subtract 1 from that power, that's negative 1/2 left. Well, now we encounter a square root of y over here. Well, y depends on x, so something does happen. We do take this derivative. It's just like the outside part of a chain rule. So here it looks kind of like what we did with the previous term. But because this was a y and not x exactly, I multiply by dy dx, the derivative of y with respect to x. That's like the multiplying by the derivative of the inside part of chain rule. Okay, over here, 3y. So I pretend like I'm taking the derivative of y, with respect to y, and I get 3. But really it's with respect to x here, so I have to multiply by dy dx. Okay, so now we have to do some simplifying, do some algebra to solve for dy dx. So I think I will go ahead and rewrite these negative 1/2 powers and multiply these 1/2s as well. So I get 4 over the square root of x plus 5 over the square root of y times dy dx equals 3 times dy dx. Okay. So next, to get dy dx by itself, I want to bring the terms involving it together, and every other term that does not involve dy dx, I want on the other side of the equation. So doing two things at once here, I'm going to subtract this from both sides to move it over. And the term that does not involve dy dx, I'm going to move over there by subtracting it. Okay. Next step, we recognize that there's a times dy dx in each term here, which means I can factor it out. And that's how we're about to get it by itself. Okay, so next up, I'm not sure if I would say that you necessarily have to do this next thing, but I think it's kind of nice for simplifying. And this is how Pearson presents their answer in the homework, too. It might be nice to get this as like a single term by getting like terms, or excuse me, a common denominator is what I mean. So if I could write the 3 as 3 root y over root y. And now that these have the same denominator, that allows me to bring this together as one thing. That does make it a little nicer in the end. So I'm going to bring those together. 5 minus 3 root y over root y times dy dx. So now this is just a single fraction, and I can divide it from both sides by multiplying by the reciprocal. And that's how we get dy dx by itself. Right, so we will get -4. And since I'm multiplying by the reciprocal of this, where these are flipped, that means this square root of y will show up in the numerator here. And we have this square root of x still in the denominator. And that'll be times this little difference here. Right, and that is the best simplification we get. All right. I'm just checking my work real quick. Okay. Let's do one involving e. So we want to find dy dx for y cubed plus e to the xy equals 1. Okay, this is an implicit relationship where y, it does depend on x, but not that nice tidy y equals f of x formula. So we do implicit differentiation, where we take d dx of both sides. And whenever we encounter a y, we treat it a little bit differently because it does not match up perfectly with that x. So I will do a power rule, 3y squared, but that's really like the outer part of a chain rule problem, so times the derivative of y with respect to x. All right, here we've got y involved as well, so we're also going to have a dy dx showing up here. Well, okay, we will take that outer derivative. Derivative of an e function is itself. But then we multiply by the derivative of the input. Well, there's still a little more work to do there. And this will equal 0 because the derivative of 1 is 0. So still a little work to do there. Notice that that's a product rule. Because y does depend on x, So this derivative will affect this part too. So it's a product rule. Let's do x times the derivative of y. That's dy dx. Plus, there's the derivative of x times y left alone. Equals 0. Okay, so now I want to get the dy dx's together and everything else on the other side. So I would probably start by distributing this e to the xy. And I would like to write the x first, x times e to the xy times dy dx. And I would like to write the y first here, plus y times e to the xy. Okay, so these I can bring together by factoring out this times dy dx. This one I would want to move over to the other side of the equation. And now we divide to get dy dx by itself. And don't worry that we have y here showing up in our final answer. X and y have this complicated relationship already, so that's to be expected. That's normal. Right now, I would like to do a tangent line problem that I've made to be a little more challenging. Excuse me. Now, I realized later that there's actually a bit of a shortcut to this one, and I'll let you know about that. But I do want to work through the more difficult full way for the sake of the practice. We want to find the equation for the tangent line. To the curve natural log of y plus x over xy squared equals 1. And you have to say what point it's at. So this tangent line, it will just glance this curve at this point 1, 1. All right, now a little shortcut approach, which I'm not going to do ultimately, but it could be helpful for you, is you could, when you have a quotient like this, you could multiply both sides by this denominator, and that does make for a little bit of an easier problem because it's no longer quotient rule. But the thing is, I wanted to practice quotient rule for this. So I'm going to do that. I'm going to walk through it for the sake of practice. So the slope of the tangent line, that's most of the work to find. Well, that's still dy dx like normal and evaluated at the point 1, 1. So what I mean by this vertical bar and writing this 1, 1 here, means once I find the derivative, we plug in x equals 1 and y equals 1. So we find the general expression for the derivative first, but then you plug in that point 1, 1. That's how you find the slope at that point. So I did want to work out the full quotient rule, but you could technically make it a non-quotient rule problem. So I'm taking the derivative of a quotient. We do quotient rule. So that is low d high, and it gets a little complicated, so I'm not going to fully calculate that yet. I'm just going to write times the derivative of ln of y plus x. So that's low d high minus high, use your parentheses. So that thing times the derivative of the denominator. I'm also going to wait to calculate that in a minute. Over low squared equals 0, as that's the derivative of 1. Now let's calculate some of those derivatives that we left. So first up, this ln of y, I'm taking the derivative with respect to x. Well, y does depend on x, so something happens here. I do the 1 over y, but then I multiply by the derivative of y with respect to x. So we're always doing that when we're taking the derivative of a y part. Well, the next one's just x, so no fancy stuff there. All right, so this is the same now times the derivative of xy squared. That's a product in there, taking the derivative of a product. So I do product rule. X times the derivative of y squared be 2y times dy dx. Plus, now derivative of x is 1 times y squared. I'm running out of space for my equals 0. And we can actually go ahead and square that. Often I just leave it written as a squared thing, but here it's pretty nice just to do it. X squared y to the fourth. All right, now we're ready to expand by distributing things. So I'm going to distribute this xy squared. Notice first it's going to bump up against this 1 over y. So that'll cancel off one of these powers of y. So I get xy times dy dx plus, now this times 1. And now we go over here. Since this will get a little complicated, I'm going to not distribute that negative quite yet, but I'm going to work this part out inside these brackets here. But it is minus this whole thing. So notice I have a sum going on in both of these. So that's a product of two binomials. It means I'm going to have to FOIL this thing. So the product of the first two And I'm going to rearrange the order of these things a little bit. Nice to write the 2 first, and then the xy. So I just wrote this part. And then I'm going to write the times ln of y, and then the times dy dx. So just did the product of these first things here, but I wrote it in a nicer order. So that's the first part of the FOIL. Next is outer. Well, I've got a y squared and ln of y. So plus y squared ln y. Okay, then inner be this x here times this thing. So plus, I'm going to need a little more space, I think. So plus 2 x squared y. I've got 2 x's here being multiplied. So 2x squared y times dy dx. And then the last part of the FOIL be x times y squared. This will all be equal 0 and over x squared y to the fourth. Okay, so took care of that. Now would be a good time to distribute this negative, and then we can see how things combine, if at all. So xy times dy dx plus xy squared. So now minus 2xy times ln of y times dy dx. That's a big term. And again, I'm distributing this minus now over all these things. So minus y squared times ln of y minus 2x squared y times dy dx minus xy squared. Now there is one really cool thing that happens here. I have a couple things cancel out actually. I have a plus xy squared and a minus xy squared. So that's pretty nice. Okay, I do not believe we have any other nice cancellations like that. Well, there is sort of a thing I can do here, and let's go ahead and do it now. This denominator here, well, because we're equal to 0, the denominator actually doesn't matter, really, because when I have a fraction equal to 0, really the only thing that can make that happen is the numerator being 0. Or you could think of it another way. I could multiply both sides by this x squared y to the fourth. That'll get rid of this fraction here. And on the other side, I'll be multiplying by 0, and that's still 0. So really, this doesn't matter. So I'm multiplying both sides. Multiply both sides by this denominator. That'll cancel it off over here and still leave us with 0 on the other side. So it goes away, essentially. So that's kind of nice. So what are we left with here? Well, at least it's no longer a fraction. And we got rid of a couple terms. Now, I think we're ready to bring the dy dx terms together and everything else to the other side. That would be just this one. It doesn't involve dy dx. Right, so the ones that do, these three terms that I'm underlining, we bring them together. We can factor out dy dx because there's a times dy dx in every one of them. So xy minus 2xy times ln of y. And then with this one here, minus 2x squared y. So all that times dy dx. I just factored it out. And this other term, this negative y squared plus ln of y, I'm just going to add y squared ln of y to both sides. That just moves that on over. And now I'm ready to solve for dy dx by dividing. Dy dx equals y squared ln of y over this big thing here. And how about I check my work real quick? That was a lot. Okay. So am I done with the problem? Well, we're pretty close, but not quite done. So let's remind ourselves, what were we doing here? The goal is to find the equation for the tangent line. So I'm trying to find the equation of a line, and we're working towards the slope here. So the slope of the tangent line, it's dy dx, but evaluated at that point. This is the point that we're at, where the line crosses the curve. So we just found the general expression for dy dx. Next step is to plug in x equals 1, y equals 1, and then we'll have the slope of the line. So plug in 1, 1, get 1 squared times ln of 1 over 1 times 1 minus 2 times 1 times 1 times ln of 1. Minus 2, 1 squared times 1. Now, what's ln of 1? Well, any logarithm of 1 is always 0. You could go back to our little video on logarithms if you're interested, if you need that refresher. So we get 0 up top. That's a times 0. And we might be in trouble if the denominator is not 0, because 0 over 0 is not a very clear form. But we do see that I get a 1 minus 0 because of this ln of 1 here, minus 2. So this does work out. This is 0 over negative 1, and that's definitely just 0. So that means the slope of my tangent line is 0. So it's this flat horizontal line, turns out. Oh, this was m, the slope, by the way. I wanted to write that. So that does give us a pretty simple form. If you have a more complicated slope, I want to show you how that works in general. So normally you would put the line in point slope form at first, at least. Since we just found the slope and we know a point as well on the line, it's that point that's given where we cross the curve. Or I should say, just touch it. It's not like you go through it, you just glance the curve. So that's the point we use for point slope form. So it's y minus the y value of that point equals the slope times x minus the x value of your point. And well, this 0 takes care of a lot of stuff, right? That'll go away. And then we can move this 1 over. Y equals 1. It's a nice horizontal line. All right, so next time we will discuss related rates. It's one real-world practical example of this stuff being applied.